Okay, so this second problem that you posted was actually something I felt a little bit more familiar with. So I actually had to type something up because it was so fun. I'm starving for mathematical problems, right? Being in sales, and when somebody posts something interesting, I just run with it. So I formulated this as some kind of minimization problem then, where S and Q are two given vectors. S1 is the big one and the Q1 is the small one, which we should then window or something like that over the set. So P will basically then shift or project then the specific part of S down to the same subspace where Q lives. Q is an M vector then, and S is this big large N vector. Yeah, better explain like this perhaps. I don't know if that's correct notation or not, but yeah, so what we need to do is then for all RKs computed like this, we should compute the minimum. So it's a very discrete kind of problem, and every RK can be computed in M ops, exploiting then there's a very specific structure to how to compute PKS. So overall that leads us to then, since how many of these RKs do we have? We have about order n of this, and we have computation is order m, so it should be mn, right? Can this be improved? Can we make this, for instance, order of n? Yes, I think we can, by using some kind of telescopic sum here, right? That we, well, it's telescopic, right? But basically, if we have RK, we can compute RK plus 1 by just adding and subtracting the edge points. I don't think that's a very nice parallel algorithm because it's super sequential, right? So how would we do that a bit more efficient, like some kind of compromise between sequential algorithm and breaking it down into independent parts? So here is my lame attempt. So suppose you divide this set of RKs into some kind of set of multiples of 32, and you compute them all in parallel. Even though we could compute R32 by just computing R1, R2, R3 in sequential, right? We do this in parallel now. And then we use the sequential algorithm to sort of fill up on R1 up to R31, and similarly for all the other blocks. And then hopefully with some wishful thinking we could then potentially compute this, I don't know about the notation here, was a bit screwed up potentially, but rho P should be the minimum then over this 32 points, right? So that, I think that should be fairly quick to do. It's a very quick reduction with shared memory. Then depending on the problem size we might need this to do some more fancy reduction over the entire set, like this. And yeah, I don't know, maybe this works, maybe this is complete hogwash made up thing that has nothing to do with CUDA programming. It would be interesting to see your explanation afterwards, how this is actually done efficiently on a CUDA. And I would like to see even a more in-depth description of what you did with the other problem there, which I couldn't really see a good direct method for, so I just tried some random search methods and they got better results. I was just, yeah, screw it, this is some kind of stochastic search method which I'm complete out of my water trying to do stochastic methods. I don't know how they work. But yeah, great. So what I wanted to say, really, not talk about this problem, but what I really wanted to say was I was serious about the YouTube thing here. I think there would be a great marketing opportunity to have a sort of recreational CUDA programming done by real CUDA experts, just tuning in for fun, to see people to get to see like CUDA programming can be fun, and like we start with toy problems or interesting problems, and we see how we do some mathematical breakdown, and then we see also some CUDA code or maybe other types of CUDA based computational systems or frameworks or languages, and yeah, just spark an interest in the community for doing parallel computing on GPUs. I think could be quite interesting. Not courses, right? Just recreational programming, tuning in, watching somebody else do all the work.